This is a photograph of the field at the Super Bowl, an environment where millions of viewers expect instant, flawless data updates. In live sports broadcasts up this scale, there is zero margin for error in graphic execution. To meet these demands, major networks are moving away from traditional hardware-heavy broadcast control rooms and the offline tools that powered them for decades. The legacy pipeline requires graphics to be pre-rendered into static video sequences. This involves a fill channel for RGB data and a separate key channel for the alpha transparency mask, which are then piped into the production switcher as two independent video feeds. This diagram shows the resulting bottleneck. If a player's statistics change or a layout needs a last-minute adjustment, the entire output stalls. The operator cannot push the graphic to the air until the compositor finishes rendering the new frames. This creates a constant friction between creative iteration and the stability required for live broadcast, as every change carries the risk of a render time delay. Unreal Engine 5.5 introduces a native motion design mode, previously known as Project Avalanche, specifically to eliminate this render time dependency. In this environment, broadcast graphics are built as drivable, real-time 3D software applications rather than static video files stored on a server. This wireframe demonstrates live data integration. Executing directly on the GPU, it instantly shifts shapes and numeric values as raw data arrives, bypassing render previews. This real-time calculation enables a continuous data flow from source to screen, completely removing the post-production rendering bottleneck. This architecture unifies the flexibility of procedural 3D motion design with the engineering rigor required for live television playout. The foundation of this procedural system is the cloner actor, directly inside the motion design viewport. As illustrated here, the cloner replicates a single mesh into a structured, multidimensional grid. This allows artists to build visual complexity at scale without manually positioning individual objects. To animate these clones, we use effectors. These function as spatial drivers of change. When this volumetric boundary sweeps across the cloner array, anything within its influence undergoes dynamic adjustments in scale, rotation, or position. By utilizing the effector delay parameter, these transitions are staggered over time. This generates fluid, wave-like motions that ripple across the entire layout, based on the index position of each clone. Version 5.5 adds features like the push-apart effector and proximity-based collision, allowing clones to interact with each other and their environment without the need for manual keyframing or complex physics bakes. This system abstracts the underlying Diagra particle simulation, providing a high-performance transform offset workflow that remains accessible to designers. Geometric complexity is only useful if the aesthetic can be adjusted quickly. Traditionally, game engine material edits require full shader recompilation, stalling the viewport. This diagram shows the material designer, which uses precompiled parameter networks to bypass those delays. When a designer reorders a layer or changes a blend mode, the system updates parameters in a master material rather than generating new shader combinations. This provides the instant feedback necessary for live show environments, where graphic updates must occur without dropping frames or freezing the UI. For temporal control, the engine uses Sequencer. The addition of non-destructive animation layers allows users to stack and edit motion paths independently, similar to the workflow found in offline animation tools. To manage rendering at studio scale, the movie render graph uses a node-based architecture to distribute render settings across entire sequences or multi-shot projects. These systems grant the iteration speed required for live television, while maintaining the high fidelity of a cinematic real-time engine. This photograph shows the environment where these graphics must survive. In a live control room, an operator needs a reliable way to trigger and manage graphics during an unscripted show. The broadcast rundown tool serves as the master interface, utilizing a dual bus structure with a preview and program channel. Operators use the preview bus to load a template and populate it with dynamic payload data, such as a player's score or a news headline, ensuring the data is correct before pushing it to the live program output. A common problem in live broadcast is graphic collision, where a full-screen graphic is triggered while a lower third is still active on the screen. As shown in this logic tree, Unreal uses state trees and transition logic to manage these overlaps. Graphics use semantic tags. If a full-screen graphic is called while a lower third is active, the system automatically executes the outro for the lower third before bringing the new element in. Transition logic turns a static animation file into a reactive playout system that manages its own transitions based on the broadcast's current state. The final requirement is physical connectivity, moving the rendered pixels from the GPU to the facility's video network. External production switchers control the engine via the Remote Control API. Tools like BitFocus Companion can capture hardware button presses and route them as OSC commands directly to the Unreal Motion Design templates. Modern broadcast facilities are moving away from traditional dual-link SDI hardware in favor of more flexible IP-based infrastructures. This diagram illustrates the SMTP ST2110 integration. Powered by the NVIDIA RiverMax SDK, the engine streams uncompressed, gen-locked pixels directly from the GPU memory onto the broadcast network. By utilizing high-bandwidth enterprise network cards and the MediaLux Video SDK, Unreal reduces video I/O latency to frame-accurate speeds. This level of IP integration allows Unreal Engine to function as a reliable, native component within the professional broadcast engineering rack. The Epic Games Sports Broadcast sample demonstrates this complete architecture in a practical production scenario. In this split view, an operator executes a simple score trigger via an external web interface. The complex 3D graphic responds by scaling up and updating its internal text fields in real time. This single event activates the entire pipeline. The state tree resolves the transition, the cloners execute the procedural animation, and the final frames are pushed out via ST2110. This process confirms that broadcast graphics now operate as live, interconnected software programs that happen to output pixels. Unreal Engine 5.5 acts as a complete structural replacement for legacy digital content creation pipelines. This architectural blueprint illustrates how the system merges procedural creative freedom with the bulletproof logic required for professional playout. Studios that do not adopt these real-time, parameter-driven workflows will remain limited by the render bottlenecks of traditional software. For the modern motion designer and broadcast engineer, mastering this unified architecture is the new mandatory baseline for high-end live production.